AI in medical imaging area. So I will introduce myself briefly. I'm directing artificial intelligence in biomedical imaging lab at Tokyo Tech. Before that, I studied medical imaging AI at Illinois Tech and U Chicago in the US for 17 years. So when you say deep learning obtained enthusiastic attention as a breakthrough technology from academia and industry around the world. Some people said AI driven by deep learning would make the fourth industrial revolution. When you say the fourth industrial revolution, it is not the matter of an individual or researcher, it's the matter of the country. So as such, every country treats AI as the most important strategic area. US is not an exception. US Congress is creating multiple AI law, and I was invited to advise the Congress as an AI expert. Since 1994, my lab has been studying actively on deep learning in medical imaging. We studied denoising in images with deep learning in 1996, semantic segmentation, end-to-end deep learning, virtual dual energy imaging, and virtual high-dose imaging for CT dose reduction. Those areas become hot topics in the recent few years. I will introduce some of them today. I will talk about today imaging of materials, in particular tissues of a human body with artificial intelligence instead of materials themselves. But I hope some of you feel my talk interesting and some of AI topics are useful in your future research. So today I will talk about our RE deep learning model MTANN and its application. Generally, AI learns human skills, but I'll talk about that first. Another groups of application that I will talk about is virtual medical imaging, where AI learns physical property of materials in imaging. Recent news of deep learning in medicine area is deep learning performance was equivalent to dermatologist in diagnosis of skin cancer. In other words, deep learning was able to learn skills from human experts. So deep learning takes inputted medical images of skins and learn their categories such as malignant benign tumors. One of Ari's deep learning model is our original MTANN or MTAN. MTAN is a massive training artificial neural network. MTAN is a supervised image processing based on machine learning model. How does MTAN work? MTAN directly learns the relationship between input images and corresponding teaching images that are ideal images for the input to enhance specific patterns such as lung cancer and suppress other patterns in medical images. The MTAN consists of linear output ANN regression model, which is capable of operating on image data directly. Input of MTAN is a pixel value in the subregion or image patch from the big input image. The output is a single pixel. So the input is images and the output is images. The entire image is obtained by scanning with the MTAN kernel pixel by pixel in a convolution manner. This is training of MTAN. Input subregions or image patches are entered as the input to the model and it outputs pixels. It compares the output with teaching pixels and calculate error between the two. Weights are adjusted to minimize this error. So after the training, it's expected to output pixels similar to teaching pixels. Let me show you some example. which is the MTAN application to medical image analysis, which learns skills of human experts. To enhance lung cancer on CT image, here we use teaching image that contain light distribution at the center location, cancer location, taught by expert radiologist. By training the MTAN with the pair of input image and corresponding teaching image, the MTAN learn to enhance lung cancer and suppress normal structures such as vessels. Here's we jump into the result. So here's a result. Here's a lung cancer in the lung. We want to enhance this. This is output image of the trained MTAN. As you can see, the lung cancer is enhanced and suppress other soft tissue such as lung vessels. Also, a large structure in the hilum remains. When we apply the thresholding, we got this binary image, and when we remove small and large regions, we detect the lung cancer very accurately. So this is the one example of our MTAN model. This is different from other deep learning model because output is images as opposed to categories such as cancer or non-cancer. We received fairly good amount of attention from media and press. The second topic in the second example of the AI that learn expert skills, which is semantic segmentation of organ. So this is left ventriculogram and of the heart, the contour traced by cardiologist in blue on the right. This is very difficult problem because some places have very low contrast and no edges. We train MTAN model with the pair of the input and teaching images to learn expert skills. After training, we got this result. As you see, the MTAN was able to enhance boundary of the ventricle, even the boundary segment without contrast here. And this is a side-by-side comparison with a conventional edge enhancer. It couldn't enhance those parts, whereas MTAN could. Once edges are enhanced nicely, we just need a simple tracing method to get the contour. Here's a result. AI contour in red agree very well with physician's contour in blue. This means that MTAN AI was able to acquire a physician's skill of segmenting an organ. So this is kind of typical application of AI. AI learns expert skills, but next topic is a unique application of our MTAN deep learning, which we call virtual medical imaging. What if AI learns physical property of materials instead of human skills in medical imaging? How powerful and useful would it be? That was a question we had. And first development of virtual medical imaging with our MTAN is a reduction of radiation dose in CT. Studies show that CT scans expose patients to cumulative radiation dose and increase risk of developing cancer. So we need to reduce radiation dose in CT. It's crucial. As you know, when radiation dose is reduced and then quantum noise associated with artifact increase in CT image like this. So there is a trade-off between radiation dose and image quality in CT. So our purpose in the study was to develop radiation dose reduction technique by using MTAN. So the idea is to train our MTAN deep learning model with ultra low dose CT with 0.1 millisievert and the corresponding teaching high dose CT with 3 millisievert over chest phantom. Once trained, the MTAN does not require high-dose CT images anymore, and it's applicable to new ultra-low-dose CT image of a patient to produce image looks like a high-dose image. That is a basic principle. So here's the result. This is image on the left is ultra-low-dose CT image with 0.2 millisievert. So you cannot see lung cancer here because of the noise and artifact. When we increase the radiation dose by a factor of 10, we get this image on the right. You see the CT image with less noise or artifact. The image in the middle is our MTA image created from image on the left. The noise and artifact were reduced substantially while improving the conspicuity of lung cancer and vessels. Here is a quantitative evaluation result. The quality of our virtual high-dose image is equivalent to 7.34 millisievert image. That means we achieved 97% radiation dose reduction with this technology. We achieved 97% dose reduction with the MTAN, whereas state-of-the-art dose reduction technology could reduce 17 to 44% of radiation dose. Translational research was done by a company called Alphamedica, which is a venture company in the Silicon Valley in the US. They obtained FDA approval of the technology in 2016. We can do a similar thing for mammography as well. So the idea is a kind of same. We train our MTAN with low dose mammography and teaching high dose mammography. And once trained, we don't need high dose mammography anymore. And it's applicable to new low dose mammograms of a patient to convert input ultra low dose images to high dose image like images. Here's the result. The half image on the left is very noisy, and we cannot recognize a tiny microcalcification, whereas our MTAN virtual high dose image in the middle contains less noise, and the tiny microcalcification here is visible, and which is similar to one in the full dose image on the right. When we did quantitative evaluation, we found MTAN achieved 89% dose reduction. To prove the image quality equivalence, we did a blinded observer rating study with 35 breast radiologists. They were asked to rate image quality of the two images, virtual and real low dose images in a blinded manner. Virtual and real high dose image in a blinded manner. As a result, 21 out of 35 preferred our virtual high dose images over real full dose images, or could not distinguish between the two. This is the last one, the final virtual medical imaging about chest radiograph. In one study, 80% missed cancer in chest radiograph overlap with ribs and clavicle. If we can separate bones from soft tissue, we can avoid those misses. So that is a motivation. So our purpose was to develop a new image processing technique to separate bones from soft tissue in chest radiographs. So we want to extract bone structures from chest X-rays. To do that, we have dual energy imaging. In dual energy imaging, patient get two X-ray exposure. One is at high energy level, the other at low energy level. We obtain two images, and by subtracting those two images with a smart algorithm, we can obtain soft tissue enhanced image and bone enhanced image. So this has some limitations. The radiation dose can be double. So we want to do the same thing by only software. To do that, we use MTAN to train to obtain dual energy soft images and dual energy bone images by using real dual energy system. Once trained, we don't need the system anymore. We can apply the trained MTAN to a single chest image from the standard system. Here's a result. You can see that the ribs and the clavicles are suppressed by using our MTAN technology. So you can see the soft tissue is enhanced and bone structures are removed. This is side-by-side comparison. The image on the right is soft tissue image created from the image on the left. This is bone enhanced image. This was done only by software, machine learning model. And compare with dual energy system, and it's enlarged. The image in the middle is MTAN soft tissue image created from image on the left, and this is gold standard dual energy soft tissue image VR1. We have cancer case here. Here's a cancer. You see that our MTAN soft tissue image, the cancer is enhanced by subtracting bone component. I will skip this because of the time, and I will jump into conclusion. In conclusion, AI can learn skills from human experts. We train MTAN for lung cancer detection, CT, and MTAN for semantic segmentation organs. Such AI technology will help physicians their diagnosis. And MTAN deep learning can learn physical property of materials in imaging, which offers virtual imaging. Virtual DNA imaging was able to separate bones from soft tissue component in chest radiograph. Virtual high-dose images was able to reduce noise, thus radiation dose by more than 90%, substantially in CT and mammography. Thank you for your attention.